Good afternoon, Professor and teacher assistants. In this presentation, we will be presenting on our machine learning project. I am Yixing and my groupmates are Cecilia So, Laura, and Cecilia Lee. Our group has chosen to do the Kaggle project on plant seedling classification. In this video, I will first talk about the application of plant seedling classification, preceded by our objective and the chosen datasets. Then I will talk about our experiments and end off with our conclusion. We have come up with a problem statement and a real-life application, which is to differentiate the desired plant seedlings from nuisance such as weed, which are detrimental to farmers and their yield. Therefore, in this project, we aim to find an optimal set of model parameters and strategies that can best classify the images into their respective classes. This was done by experimenting the following and will be elaborated in this video. First, let us explore the plant seedling dataset. In this project, we took the plant seedling dataset from Kaggle. There are a total of 12 different species of plants, with 4,750 training images and 794 test images. As you can see from the pie chart, there is an uneven distribution of images for each class, with plant types like maize and common wheat having the lowest proportion. Furthermore, the quality of each images varies, with some having higher resolution than the others. Some of the leaves were taken in soil background with low brightness, making the leaves less visible too. To add on, there were some seedlings that looked fairly similar to one another, like blackgrass and the loose silky band seedling. All these could potentially decrease the accuracy of the model due to low quality input training data. To increase the quality of our input data and solve the problem of unequal image representation of each class, we will have to do some data preparation before training our model. There are 4 main steps we would take during data preparation. Firstly, we will do image segmentation to ensure the seedlings are visible to the model. Then we will do data balancing to ensure equal representation of all classes, therefore preventing a skewed model. Then we will do some data augmentation to increase the data size, therefore allowing for a deeper model to be built. Finally, we will do some data pre-processing to ensure the images can be fit into our models. Since the images are taken from different environments, the images might contain a lot of noise. There are also certain species like the blackgrass and loose silky bands with very thin leaves. Thus, the model may not be able to differentiate these species if we do not segment these images. Therefore, we use hysteresis thresholding to check if we were able to obtain the masked images that generalizes well across all images. To get the hysteresis thresholding, the first thing to do is to pixel sampling from random images from the different classes. As seen from the pixel sampling, there was a lot of brown color which could be attributed to the soil, barcode, and rocks present in the images. Next, we can convert the images into RGB and plot the distribution. However, as we can see from the RGB plot above, a larger number of colors are concentrated together. Hence, we have converted the RGB image into HSV, which allowed for a more distinct threshold. There are 2 ways to segment images. First is all together with the same HSV value, and second is individually class by class with different HSV value for each class. The reason why we tried segmenting the images individually class by class is because we found out that the HSV range for every class is different. Thus, this results in some noises in the segmentation of images. However, we are not very sure if by doing this, will the model be able to generalize well. Thus, this will be further elaborated in one of our experiments in the subsequent slides. There needs to be data balancing as the different class sizes may cause biasness in the model train. There were 2 data balancing techniques which we tried, namely modifying weights and increasing image counts. Initially, all classes have equal weights. However, due to the imbalanced dataset, we would like to modify the weights to take into account these differences. We calculated the inverse document frequency of each class and normalized it. This ensures that the classes with lower representation had higher weights. For example, common wheat and maize have lowest representation, so they have the highest class weight. Next, to increase the sample size, we could also do some data transformation and augmentation to the original images. For example, we did some shear and shift to the images. We increased the count to 700 images per class with this technique. Other data processing methods that needs to be done before we can fit the images into our model include sharpening of image. Since some of the images were so blurred, we will use a filter to sharpen our input images. Then we will also resize our images, since for some transferred learning models, they are trained on particular image sizes. Finally, we would need to split our dataset into 5 folds for our training. This will help us train a more robust model and help increase accuracy. Now, I'll talk about the experiments we did. To ensure we get the highest accuracy in our model, we will ask ourselves 4 main questions. Firstly, does pre-processing help increase accuracy? We will want to compare the results of using raw images against pre-processed images to see if there's actually a difference in the accuracy score. Then, we will want to see if we should segment the images individually or all together. We found out earlier through HSV visualization that the classes have unique distribution. Therefore, we will want to know if we should segment the classes using only a common HSV range, or should we segment the classes according to their unique HSV range? Thirdly, we want to see if we should use data augmentation or weights to take into account the differences in class representation. Since both methods can be used, we will see if there's a difference between these two methods. Finally, since there are many pre-trained models available now, we want to see which is the most optimum for our use case. For this model, we trained it using a simple 3-layer convolutional neural network and added a final softmax layer with 12 outputs. This is a graph to compare the results of using raw data against pre-processed data. As seen from the graph, when training on raw data, there is an overfitting of the model. After a while, there is a plateau in validation accuracy. However, when trained on pre-processed data, there's an increase in accuracy and the model did not overfit. Thus, this shows that pre-processing is important and we should use it for the rest of our training. Now, we would like to compare the results of models that were being trained by images segmented individually against those that were segmented all together. Images that were segmented individually meant that the classes were segmented according to their unique HSV range, while segmented all together meant that the classes were segmented according to a common shared HSV range. As seen from the segmented individually score, it has a higher validation accuracy and a lower validation loss. However, it has a lower Kaggle score. This could mean that the model was trained and fitted for that particular data set. While for the segmented all-together side, they had a higher Kaggle score despite losing out in validation accuracy and loss. This means that using images that are segmented all together is better, as it generalizes better to more unseen data which may not be properly represented in our training dataset. Thus, in our subsequent models, we will use classes that were segmented all together. Next, we will compare against the 2 different methods to tackle imbalanced data. The first method is using data augmentation, meaning flipping and rotating images to create more data. The second is using weights, meaning that we would normalize the dataset and use weights to take into account the difference in data size, with clusters of lower representation having higher weights. As seen from the graph, models that were being trained with 700 images per class seems to be overfitted, with high training accuracy and low validation accuracy score. As the same exact parameters and hyperparameters were used to compare between these two, we suspect that there is not enough hidden unit in the dense layer after the pre-trained model, as there are 700 images per class and thus more parameters were needed. Thus, the model being trained using weights had a higher validation accuracy and Kaggle score. With this, we will move on to conduct our subsequent experiments by modifying weights, as we also realize that the other models take a significantly longer time to train. We used 4 different pre-trained models in our example. We chose the 3 most popular transferred learning models, namely ResNet, Inception, and Exception. They were smaller models as compared to other models like VGG19, which has much larger parameters. Let us start to dive in and explore the various transfer learning models. We will compare the 2 ResNet models, ResNet 50 and ResNet 50 V2. They are similar models. The main difference in the 2 models is the way in which they calculate the propagation of connection between blocks. As seen from the graph and scores above, it can be seen that ResNet 50 V2 has a higher accuracy compared to ResNet 50, which is quite expected. We also tried on the other transfer learning model, Exception. The Exception model is an improved version of Inception V3. It consists of regular convolution and depthwise separable convolution operations. After trying on different hyperparameters, the best model we got is to add a flattened layer, 2 dense layers with 512 units, 1 dense layer with 256 units, and 1 output softmax layer on top of the exception-based model. Unfortunately, the accuracy is low compared on other models, which only got around 96% accuracy on validation data and around 94% Kaggle F1 score. Finally, we tried the other transfer learning model, Inception ResNet V2. It's a convolutional neural network with 164 layers and is built on the Inception family. However, it incorporates residual connections. As seen in the graph above, a very simple model with only one hidden layer has resulted in a validation accuracy of 97.7% and a Kaggle score of 96.8%. Now, let us move on to compare all the different transfer learning models. As seen from the summary score above, it can be seen that using the Inception ResNet v2 model gave the highest validation accuracy, lowest validation loss, and highest Kaggle score. Therefore, we will pick Inception ResNet 2 for further fine-tuning to improve the accuracy of the model. Let us explore different ways we can tune the hyperparameters of this model to increase the accuracy. There are four main things we can do to increase the accuracy for the model. Firstly, we can increase the dimension of the data. This is to provide more information of the images to the model. Thus, this could allow for better feature extraction during the training phase. In this experiment, we changed the input data from a size of 2562563 to 2992993. However, since increasing the image sizes increases the computing time, we did not choose to increase the image size further. Secondly, we can reduce the batch size. As proven, smaller batch sizes tends to allow model to generalize better. Thirdly, we can adjust the learning rate. This will determine how much rate will be updated during the training. And finally, we will do fine-tuning to increase the accuracy of the model. In fine-tuning, we will be tuning quite a bit of parameters. We will talk about fine-tuning now. There are around 200 convolution layers. In pre-trained models, the initial layers detect simpler and more general patterns. As the layers get deeper, the more specific to the dataset and the more complicated the patterns they detect. Thus, using this, we will try to unfreeze the last n layers. This is done so as to find out unfreezing how many layers will allow the model to learn the best. First, we will test out how many layers we should unfreeze and train the layers on. Unfreezing the layers makes these layers trainable and thus causing its weights to change. As seen from the table above, the optimal number of layers to unfreeze is 17, which means we would unfreeze from convolution 383 onwards. Next, we'll be adjusting the batch sizes. By adjusting the batch size, we'll determine the rate at which the gradient descent occurs. If too large batch sizes is used, it will lead to poor generalization of the dataset. However, if too small batch sizes were used, it could cause the model to bounce around the global optimal. In addition, it will lead to slower training of the model since more updates of the weights are being done. Therefore, an optimum batch size must be chosen. In the case, it can be seen that choosing a batch size of 32 provided the best validation accuracy, lowest validation loss, and highest Kaggle score. Therefore, we would choose to use batch size 32. Learning rate would determine the magnitude that the weights are being updated during rating. It controls how quickly the model is adapted to the problem. Larger learning rate will result in more repeat changes, which can result in the model to overshoot the minimum and fail to converge. However, a low learning rate will cause the gradient descent to be very slow, therefore needing more epoch and to reach the global minimum. As seen from the table above, the optimal learning rate that allows for best Kaggle score is 0.0001. We have decided to remove data augmentation techniques as it is not useful in the stage of fine-tuning. After adjusting the hyperparameters of the Inception ResNet v2 model with the optimal hyperparameters, there was an increase in maximum validation accuracy, decrease in validation loss, and a 2% increase in Kaggle score. Let us move on to some of the challenges faced in this project. Some of the challenges faced include similar looking plants. There are two particular classes of seedlings that looks very similar to one another and seem to be wrongly classified quite frequently. They are loose silky bands and blackgrass. This can be seen in the confusion matrix where the main error in classification is these two classes. Second challenge is the lack of images to train on. There were some plants with fairly little representation. Using weights to train these classes helped to increase accuracy. However, due to the lack of data, a deeper model cannot be built. Since images were of low quality, even if data augmentation is used to create new images, it will not result in improvement in accuracy score. For area of improvements, there are three main things that can be done. Firstly, we can train on other larger pre-trained models like the VGG19. Secondly, we can try to use ensemble learning. In this process, we will aggregate the prediction of multiple models together, therefore allowing to build a more robust model. Thirdly, we can use SMODE to address the problem of imbalanced dataset. The difference between SMODE and data augmentation method is that SMODE creates synthetic images from minority classes based on original images. It focuses on feature space to generate new instances. Therefore, it can potentially create better quality images as compared to the images that were created through data augmentation. As mentioned before, further data augmentation techniques is not explored due to training time. However, it seems to produce quite good results as well. Thus, with more computational power and time, it's a good area to explore, and we can analyze the two different data imbalances techniques in detail. That's all for our project on plant seedling classification. Thank you very much for your kind attention.